Assalamu alaikum. So last time, Shabab, we talked about introduced to the first law of thermodynamics, and we said energy input, the first law of thermodynamics to the system applied to any thermodynamic system will be energy input minus energy output equal to the change of energy of the system. And we have went actually through this term, and we have defined this term. If we have a system undergo, let's say, a process or a change from one initial state to a final state, we said actually the change of energy of the system, this term will equal to the final energy minus the initial energy, or we can call it actually as 2 and 1, so it will equal to the final energy E2 minus the initial energy E1. And we said the forms of energy that can possess, this should equal to actually the internal energy, so this term E2 minus E1 will equal to the change of internal energy plus change in kinetic energy plus the change in the potential energy. And we have defined this term for a system. It will equal to mass. We said we are concerned with the specific property, so we have to multiply by mass multiplied by the specific internal energy, plus half mass multiplied by V2 squared minus V1 squared, plus mass multiplied by G multiplied by the change of elevation Z1 minus Z2. And this term actually will give us the total change of energy of the system, undergo actually any process from initial state to a final state, from a state 1 up to state 2. And we said also last time that most of the closed system are a stationary system. So for a stationary closed system, those terms actually two terms, kinetic energy and the potential energy, those two terms actually will equal to 0. And for a stationary closed system, we can say actually that the change of energy of the system, delta U of the system, would equal to the change of internal energy M multiplied by mass multiplied by U2 final internal energy minus final internal energy and U2 minus U1. And we said those U2 and U1 will be defined as the initial state and the final state. Those values, inshallah, will be able to calculate from the table. And this specific energy is calculated in kilojoule per kilogram. Inshallah, in chapter 3, we will learn how to calculate those specific property U2 and U1. So this is actually all what we can say about this term in the first law of thermodynamic equation, that the change of energy of the system will equal to the change of internal energy plus a change in kinetic plus the change of potential energy. And in case we have a stationary closed system, the change in kinetic energy and the change of potential energy will equal to 0. So this right-hand side term will be just reduced to mass multiplied by the change of a specific internal energy. Right, what about those terms, Shabab? We said those terms actually are the forms of heat transfer either into the system or leaving this system. And we said energy can transfer by heat, energy can transfer by work, and energy can transfer when we have mass transfers, and we can actually have energy transfer by mass. Right, let's look at actually those forms. Let's move to the left-hand side actually of this equation and see what are the forms of energy transfer in terms of heat, in terms of work, and in terms of energy transfer by mass transfer. So the forms of energy transfer. So as we said, we can have actually energy transfer by heat. Whenever actually we have temperature difference between two systems that are in contact with each other, we have delta T, then in this case we can have energy transfer by heat. Heat has a symbol actually Q capital, and it is calculated in kilojoule. Also, we are concerned actually with the specific heat, which is Q small. Q small actually is the specific heat, which is the total heat per unit mass, calculated in kilojoule per kilogram. Also, we consider this symbol, the rate of heat transfer, Q dot, which is actually the total heat transfer over a time slot, actually delta T, which is Q over delta T, which is in kilojoule per second. So this term should be calculated in kilowatt. So either we have Q, the total heat transfer in kilojoule, or we have a specific heat transfer Q small. I think your background is Q small is actually the heat per unit, heat flux per unit area. But in this course, this Q small is the heat transfer per unit mass, which is kilojoule per kilogram, or we can consider the rate of heat transfer Q dot, which is Q to total heat transfer divided by the time delta T. Also, the second mechanism of forms of energy transfer, energy can transfer by work. It has actually the symbol W capital. And we said actually whenever we apply a force, either mechanical or electrical force, and we have a movement, let's say we have this body and we apply force, so this body has moved actually a distance L, then in this case actually the work, total work will equal to the force multiplied by the distance L. Or we can use actually the specific work, W small, will equal to the total work divided by mass, which is calculated in kilojoule per kilogram. Or we can use actually the rate of work done, W dot capital, which is actually, we call it as the power of the system. Power is the rate of work done, which is the total work applied over a system through a certain time delta T, which is actually calculated in kilojoule per second, which is in this case, we call it as kW. So those are actually the terminologies associated actually with the energy transfer by work. The last term actually for the energy transfer, we said also energy can transfer when we have mass transfer. If we have, let's say, a flowing fluid inside a tube or something, as we said last class, actually, if this flow has a velocity, so it should have kinetic energy. So the energy due to actually mechanical energy of the fluid, which is part of the energy transfer by mass, equal to the kinetic energy, plus this flow actually has a pressure. So to move from one location, from one cross-section 1 to cross-section 2, in this case B1 should be greater than B2, then we have what's called actually the flow energy or the pressure energy, plus actually we have also the potential energy. And this is actually the mechanical energy of the fluid. And we said actually delta E mechanical, the change of mechanical energy of the fluid when this flowing undergo a process from initial state to a final state, from state 1 to state 2, will equal to the change of flow energy, which is B2 minus B1 divided by rho, plus a change in kinetic energy B2 squared minus B1 squared divided by 2, plus J multiplied by Z2 minus Z0. And we said the power of the fluid, power of the moving fluid, and we have applied this actually to calculate the power of hydraulic turbine. This power should equal to the mass flow rate of the fluid multiplied by delta E mechanical. Okay, E mechanical is the mechanical form, is the mechanical energy of the fluid, of a flowing fluid that can be converted to work. So if we have this flow is going with high velocity, we can generate work. We can have actually a hydraulic turbine, which is actually an impeller with blades. Then this high velocity it will hit the bucket. Then actually we can have actually the shaft of this turbine rotating. Then in this case, we can generate actually a power or mechanical shaft power using actually the mechanical energy of the fluid. And we said the mechanical energy of the fluid is part of the energy transfer by mass. So what is the total energy transfer by mass, Shabab? Energy transfer by mass, inshallah, we'll talk about this later on. Energy transfer by mass, the total value is equal to the mechanical energy of the fluid plus the internal energy. So the energy, the total energy transfer by mass will equal to the mechanical energy of the fluid, which is kinetic energy plus flow energy plus potential energy, plus this fluid actually has also a temperature. So that means it has also internal energy. Then in this case, to calculate the total energy transfer by mass, it should equal to the mechanical energy of the fluid, E mechanical, which is the part of the power that can be converted to work, plus the internal energy, which is the static energy. It cannot be converted to work. Okay, and these are actually the forms of energy transfer that we are going actually to deal when we apply actually the first law of thermodynamic, energy in minus energy out equal to the change of energy of the system. Let's get back to the slide we have here. Let's talk first of all about heat. We said actually we can have energy transfer by heat whenever we have a temperature difference between two systems, like actually this soda inside the room at 25 degrees C. This soda, if it is at 25, then in this case we don't have temperature difference. Then in this case the heat transfer will be 0. As the temperature difference increase, let's say here in this case it is 15 at 15 degrees C, then the heat will be transferred from the surrounding air to the soda at a rate of 8 joule per second. If this soda is existing at lower temperature, this means we have higher delta T, 25 and 5, then in this case we can have higher rate actually of heat transfer. So the heat transfer is mainly function of delta T. As the temperature difference delta T increase, so the heat transfer rate will be increased. For a closed system, we said the closed system, we don't have actually, in this case actually mass transfer, so we don't have this term which is energy transfer by mass. This term actually is 0 for the case of the closed system. But otherwise, actually a closed system can have energy transfer by heat, and also it can have energy transfer by work. Here are actually the terminologies that we are considering. Here is a simple example. The total heat transfer is 30 kilojoule for a mass actually of a system 2 kilogram in a time slot equal to 5 seconds. Then we can calculate Q dot, which is heat per unit time. 30 divided by 5, it will be 6 kilowatt. We can calculate the specific heat, which is the total heat, 30 kilojoule divided by mass, which is 2. Then we can get it actually as 15 kilojoule per kilogram. If we said actually we have a system, adiabatic system, as we said, means actually the heat transfer to this system is equal to 0. But we have to keep also in mind that heat transfer is a boundary phenomenon. Actually, heat or energy can only be recognized as heat. We can call it as heat only at the boundary of the system. Otherwise, when it is actually inside the system, we call it actually as part of the internal energy of the system. When it is actually transferred to the other system, we call it actually as part of the internal energy of this system. So energy is recognized as heat only at the boundary of the system. Let's consider this hot potato. Let's say it has actually internal energy of 2 kilojoule thermal energy. If it is actually existing in an environment at lower temperature, then in this case the heat will be transferred from this hot potato to the surrounding air. When this heat is inside the potato, we call it as internal energy. But when it crosses the system boundary, while it is crossing the system boundary, we call it as heat transfer. So in this case, we call the energy as heat when it try to cross the system boundary. But once it is transferred to the other system, then in this case actually we call it as part of the internal energy. So system cannot possess actually heat, but it can possess energy or internal energy. Okay. Here is actually something behind actually the theory of heat transfer. There was actually a wrong theory, which is actually the caloric theory. This caloric theory actually, it says actually there is actually a caloric fluid to flow from the hot fluid to the cold fluid in order to have the heat transfer from the hot fluid to the cold fluid. Or heat is transfer in the form actually of a caloric fluid from the hot body to the cold body. And this theory actually was totally wrong. And this theory actually was modified by what we call actually the kinetic theory, which is actually the proper one. Kinetic theory said actually molecules are tiny balls and they actually possess kinetic energy. And at the wall interface here between the hot body and the cold body, just this kinetic energy of hot molecules, which are very active, this kinetic energy is just transfer actually to the less active molecules in the colder body side. In the side actually of the cold body, and in this case actually by this way actually the heat is transferred. So at the end it is just the kinetic energy of the molecules at the interface, at the wall of interface between the hot body and the cold body is just to transfer this kinetic energy is transferred from the hot body, the molecules of the hot body, to the molecules actually of the cold body. And this is based on actually what we call the kinetic theory, but we don't have any kind of fluid that are actually transferring from the body to the cold body. So what are actually the forms of energy transfer by heat? So energy can transfer by heat in different form actually. It can transfer either through conduction or by radiation, or heat actually can transfer through convection. So heat can transfer by conduction, convection, and also heat can transfer by radiation. And I think you have an idea about this. Heat transfer by conduction in solid and still fluid, and heat transfers by convection from solid hot body to a cold fluid around, and heat transfer by radiation between any two systems of different temperature. So the mechanisms of heat transfer. So we have three mechanisms for the heat transfer, energy transfer by heat. Heat can transfer by conduction in solid and still fluid, not moving fluid. So in this case, heat can transfer by conduction. Heat can transfer by convection in between actually solid, from solid to fluid body around, and heat can transfer by radiation, and actually anybody existing at temperature greater than absolute 0 Kelvin can emit heat actually by radiation to another body existing at lower temperature. Okay, but let's consider each mechanism. Heat can transfer by conduction in solid system. Let's say we have a wall of something. This wall have actually a width, let's say delta X. The surface temperature of this wall T1, the left-hand side wall, and the right wall actually is at temperature T2. If T1 is greater than T2, then in this case, we should have actually heat transfer by conduction from the hot surface to the cold surface in this case. And this rate of heat transfer by conduction will equal to minus K, which is the thermal conductivity of this wall, of the material of this wall, multiplied by area, multiplied by delta T, the change of temperature delta T over the thickness, which is delta X. This K is the thermal conductivity of the material of the wall, calculated in watt per meter per Kelvin. Okay, if this thermal conductivity is high, like for steel and solid material, then in this case actually the rate of heat transfer will be higher in this case. And this area actually is the area that is normal to the direction of the heat transfer. So if the heat transfer is moving in this direction, so this is the area that is normal actually to the direction of this heat transfer. And this delta T is just the difference T2 minus T1. But T2 is less than T1, so this term will be what? Will be negative value. Negative with negative, then in this case the heat transfer should be a positive value. So this negative sign in this law is just an indication about the direction of the heat transfer, which should transfer from the high temperature T1 to the low temperature T2. Also, heat can transfer by conduction in a still fluid. So in countries like Canada or something, I was very close there. If you have a window or something, and inside here this window is separating a room in your house or something, which is existing, let's say, at 25 degrees C, maybe the temperature of the surrounding outside, it may approach actually minus 40 degrees C. So in this case, this is the window. We have to design it very carefully in order actually to reduce the amount of heat lost from this house to the surrounding. Then in this case, they consider the window as we have glass wall here, and this is actually a glass, and in between here, between the two walls, we have actually still fluid. Maybe actually in most of the cases, it is actually air. So when the heat is trying to transfer here, it should pass actually through this layer of still fluid, which has actually very low thermal conductivity. So the thermal conductivity is very low. And this is the idea. If we have low thermal conductivity, that means the rate of heat transfer in this case should be very low. So heat can transfer by conduction in solid and also in still fluids. And also heat can transfer by convection if we have solid surface existing actually at Ts surrounded by a fluid. This fluid actually is existing at temperature T fluid. Then in this case, if T solid is greater than T fluid, in this case actually we should have heat transfer from the hot fluid to the cold fluid. And as you know, this heat transfer Q dot will equal to the convection heat transfer coefficient H multiplied by area multiplied by T surface minus T fluid. And this is actually the heat transfer by radiation. H is actually the convective heat transfer coefficient. It should be calculated in watt per meter square per Kelvin. Okay, and based on this heat transfer coefficient, we can calculate actually the heat transfer. And we have actually two mechanisms for the heat transfer by conduction, heat transfer by convection. We have what we call actually the natural convection. This is what we called about the heat transfer by conduction minus Ka delta T by delta X. Heat transfer by convection is H multiplied by area multiplied by the temperature difference Ts minus T fluid. But we have two mechanisms for heat transfer by convection. We have natural convection, which is the natural cooling process, and we have the forced convection when we cool down a body like a hot body, a hot egg or something, using the forced air, or forces air in this case to go with higher velocity. Then in this case the convection heat transfer coefficient will be higher, and in this case actually this hot egg will be actually cooled down in a shorter time. So natural convection, we just put it in the air, and in this case the air will get in touch with this hot egg. Its temperature will be increased, so the density will be reduced. So the hot air will be going up and the cold air will be going down. So the air will just circulate around this hot egg until actually it cools down. So in this case, the convection heat transfer coefficient H in natural convection will be a little bit low. So in this case, it will cool down in a longer time. Unlike actually the case of forced convection, the convective heat transfer coefficient will be high, and in this case, we can cool down a body in a shorter time. The last mechanism actually for heat transfer is the heat transfer by radiation, and we said any body existing at temperature greater than 0 Kelvin, then in this case actually it can emit heat by radiation to another colder body. And the heat transfer by radiation is equal to sigma Stephen-Boltzmann constant multiplied by epsilon, which is the emissivity, multiplied by the area, multiplied by the surface temperature to the power 4, minus the surrounding temperature to the power 4. This sigma is the Stephen-Boltzmann constant for heat transfer by radiation is 5.67 10 to the power minus 8 watt per meter square per Kelvin to the power 4. You have those data. Area is the area normal to the direction of the heat transfer. Epsilon actually is defined as the emissivity of the body. Emissivity actually should have a value. This parameter epsilon is greater than or equal to 0 and less than or equal to 1. This epsilon parameter represents actually the fraction of the heat absorbed by a given body, because actually a given body does not absorb all of the heat actually coming by radiation. It just absorbs part of it depending on actually the properties of this body. So the epsilon represents actually the fraction of the incoming heat that is absorbed actually by a given body. This epsilon actually is equal to 1 in case of black body. So this epsilon, just over there, border. So this epsilon is almost, we can say it is very close value to 1 in case when we have actually a black body. So black body actually absorbs actually most of the heat, or we can say it absorbs all of the heat actually incoming to this body. That's why it is not preferred to have a black car or something, because black car will absorb actually all of the heat coming from the sun by radiation. And in this case, it will heat up actually the body of your car. Heating up the body of your car, then I have to actually run the air conditioning system for longer time and at higher load in order actually to cool down this car. And actually to run the air conditioning system, and in this case, you have to consume more fuel in this case. So black body has emissivity very close to 1. Type here also we said the energy can transfer by work. So this is all actually what we can say about the energy transfer. About the energy transfer by heat. Energy can transfer by conduction in solid and still fluid. Energy can transfer by convection from solid to a fluid body around, and heat can transfer by radiation. And those are actually the equation of energy transfer by heat. And this is the mechanism of energy transfer by heat. We said also energy input or output from a system can transfer by work whenever we apply a force and get a movement then in this case we can have energy transfer by work. But when it comes actually to substitute in the first law equation, energy in minus energy output is equal to the change of energy of the system. We said energy input minus energy output. This actually can be heat, can be work, or it can be energy transfer due to mass transfer in this case. So this is the form of the first law of thermodynamics. Energy in minus energy out is equal to the change of energy of the system. And this can be heat, it can be work, or it can be energy transfer by mass. But actually this heat or work, either into or leaving this system, it has a direction. And when we substitute to the first law of thermodynamics with the value, it has to be either positive or negative value depending on its direction. So we have what we call actually the sign component. The sign conversion for heat transfer and work when we substitute in the first law of thermodynamics. So if we have a system, if heat actually is added to this system, then in this case we have to substitute this heat transfer into the first law equation with a positive value. Okay, if 10 units, then I will substitute heat transfer equal to 10 units. Right. This is if heat is added. But if heat actually is rejected from this system, Q rejected, then in this case we have to substitute the heat by negative sign. If the heat equal to 10 units, so when I come to substitute here, I will put it actually as negative 10 or minus 10. So heat transfer has a direction, either added or rejected, and depending on which actually we have to substitute with its sign in the first law equation. Unlike actually, or the opposite to this is the work. If the work actually is produced from the system, work is produced, then in this case we have to substitute it with a positive sign, like a turbine. Turbine actually is a device that produces actually mechanical shaft power. So the idea of the turbine, like hydraulic turbine, we have a flow of high pressure, high temperature, then we pass it through a nozzle, we convert this flow energy into kinetic energy to hit the bucket of this turbine, then we can have shaft power. So we convert the flow energy into shaft power, mechanical shaft power in case of turbine. So turbine gives us actually work out in terms of mechanical shaft power. Then in this case, if we have a turbine and we apply actually the first law of thermodynamics, then the sign of the work of this turbine should be a positive value. But if we have a pump or compressor, in this case actually this work is consumed, and in this case we have to substitute it in the first law equation with a negative sign. This is in case if we have system like pump or we have actually a compressor. Compressor and pump are actually the opposite of the turbine. In case of turbine, we convert the flow energy in terms of high pressure into mechanical shaft power, but in case of compressor or pump, in this case we do the reverse. We convert actually the mechanical shaft power input to the pump or the compressor. We convert it actually into flow energy in terms of higher pressure. Okay. Here is just a simple example to know the difference. W capital is the total work mass given, delta T is given, then we can calculate work dot, which is the work per unit time, or the specific work, which is the work per unit mass. And this is something very simple, you can follow it. So what about the heat transfer and work? We have we have to give this before we end up with today's class. Heat transfer and work, heat and work. Heat and work actually both of them are boundary phenomena, so only energy is recognized as heat or recognized as work only at the boundary of the system. Otherwise, it is part of the internal energy of the system. And when it is transferred, heat is transferred to another body, it becomes actually as part of the internal energy. So heat transfer and work are just boundary phenomena. Only we can recognize the energy in the form of heat or in the form of work only at the boundary of this system. Otherwise, they are actually part of the internal energy of this system. Okay, so system cannot possess heat or work, but it can possess what? It can possess energy in the form of the internal energy. Also, both heat transfer and work are actually are actually associated with a process. We cannot generate a heat from the system, we cannot have heat transfer from a system, or we cannot generate work for a system at a given state. This system has to be actually undergo a process or a change from one initial state to a final state in order to have heat transfer or work. But let's say we have a system, let's say undergo a change from one initial state 1 to a final state 2, okay? In this case, if I want to calculate the work for a closed system, work is equal to, as we said, the force multiplied by distance. This force, we can say pressure multiplied by area, which is the force multiplied by distance A. A multiplied by L is the volume, so the force, the work will equal to pressure by volume in this case. But in most of the cases, pressure is not function, usually is not constant. Usually pressure is function of the volume. Then in this case, in order to calculate the work, we have to integrate BdV from V1 up to actually V2. So for a closed system, work is equal to integration of BdV. But let's look at actually the area under this curve. If we want to calculate the area under this curve, I will just take an element here. This element has width equal to delta V, and it has height actually equal to V. Then in this case, delta area of this element will equal to the pressure B multiplied by delta V. But if I want to calculate the whole area under the curve for the process from 1 to 2, then in this case we have to integrate. So the total area will equal to integration of what? BdV. So the area under the curve on the BV diagram is equal to BdV, which is the same as what? Same as the work. So the area under the curve on the BV diagram, just to give us indication about what? About the work done by this system. And that's why we said we cannot generate actually work from a system at a given state, because at a given state, the area under the curve is equal to 0 in this case. So we should have a process in order to generate work from the system. And the area under the curve on the BV diagram give us indication about the value of this work. And that's why we call the work or heat transfer our best function. They are depending on the path followed from the initial state to the final state, or the relation between pressure and volume. So if we have another relation for different paths for this process, let's say for this actually second path, in this case actually the area under the curve will be different, and in this case the value of the work itself will be different in this case. So work is a path function, like the heat is a path function also. They are depending on the path followed from the initial state to the final state, or the relation between pressure and the volume. This is unlike actually the case of properties. The case of properties are point function. So if I need to calculate the change of volume, so it will equal to delta V will equal to just integration of del V from V1 up to V2. So it will equal to just V2 final volume, V2 minus the initial volume V1. We don't care actually about the path followed. So the change of volume will equal to V2 minus V1. But this is actually unlike the case of work. Work is equal to integration of BdV. So in this case, it depends on actually the path followed to reach actually the final state. And that's why we have different systems can have actually different work depending on the relation between pressure and volume, or depending on actually the path followed from the initial state to the final state.